Good evening, and a very happy New Year to you all. I wonder what 2008 is going to bring. Time will tell. Well, we're going to begin very near home. As we know, our sun's solar system contains a lot of things, mainly the 8 planets, and Mars came into our position a little while ago, and we're going to talk about Mars later on. But also, as well as the planets and their satellites, there's a great deal of what we may call cosmic debris, comets, meteorites, and so on. And that debris we're going to talk about this evening. First of all, we come to comets. And with me I have 2 experts, Dr. Simon Green and Mr. Greenwood. Welcome to the programme. Now, comets, your field. We've got a very curious comet, Holmes Comet, discovered way back in 1892, comes back every 7 years or so, and is usually very faint, but this time it's really given a surprise.
It has been a surprise, yes. It's about 1 million times brighter than people would have expected it to be. In October last year, there was a sudden brightening of the comet, almost overnight, until it became a very prominent naked eye object.
It was in Perseus and it altered the entire look of that part of the sky.
Yes.
I made a magnitude 2.5 at one stage.
Yes, very comparable with the brightest stars in Perseus, and you only had to just look at the constellation and you could see this apparent new star there.
Now, what caused this?
I wish I knew, Patrick.
Yeah.
I have no idea. Our old view of a comet of being an icy object with exposed ices vaporizing when the sun heated them is clearly, from our images of the few comets we've seen close up, not the case. There is over most of the surface this crust, and so whatever produces the activity is happening either underneath it or percolating through it or through fissures in it. So when there's a very big outburst, it must be some violent event which is releasing material very, very quickly.
And the comet is now larger than the sun. What's going to happen to it?
On an astronomical time scale, its time is almost up if it stays in its current orbit, because gradually the ices will evaporate. It will either break up, disappear completely, or it may be just the debris left on the surface will choke off the activity, and it will just become a small, inert, rocky object. And
another comet too, Tuttle's Comet, appeared just about 13 years, and that was naked eye visibility, just about. It passed very close to the pole star at the end of December, and it now moved down into the constellation of Pisces, and moving fairly rapidly.
Yes, this is a particularly favourable apparition because comets have eccentric orbits. There's a possibility that, and in fact it's almost always the case, it seems, that their closest approach to the sun is when we're on the other side, and so they're very difficult to observe. But this particular comet is nice because its closest approach is slightly larger than the distance of the Earth from the sun, and this time it occurs when they're more or less lined up, so we can see it away from the sun and very, very well placed.
Well, of course, these really brilliant comets come back only occasionally, and we haven't had any, well, no really brilliant comets recently, but they might appear at any time.
Yes, so the last one people will, I'm sure, remember is Hale-Bopp.
Yes.
And this is a very different kind of comet. The comets we've just been talking about are ones which have orbital periods of a few years or a few decades, and they're orbiting all the time within the planetary regime of the solar system. But there are others which have orbital periods which are timed in millions of years. And these only, of course, very rarely come into the inner solar system and are seen as active comets. Almost their entire lifetime is spent at very large distances from the sun, out in the cold outer reaches of the...
And occasionally a comet bright enough to be seen in broad daylight. I've never seen one of those.
I haven't either.
And we now have samples from a comet, the Stardust mission, and that was a fascinating project, was it not?
Yes, this was the Stardust mission. This was spacecraft which flew past Comet Vil 2, flying past at 6 kilometres a second, which in cosmic terms is relatively slow. You would completely destroy your sample if you just tried to catch it. So you need to decelerate it gradually and use a low-density material. So it's a foamy glass, very, very low density. And that was then collected and brought back to the Earth.
So you had material from a comet. Was it what you expected?
Well, I think the results were quite surprising. When the material was analysed, they found that in it were high-temperature minerals, and these are similar to some of the minerals that you find in meteorites. But they must have formed very close to the sun. And, of course, the comet itself has an origin in the outer part of the solar system. So what this showed was that material in the early solar system that formed close to the Sun was being mixed to the outer reaches of the solar system and obviously then incorporated into comets. And that was a wholly unexpected result, I think.
Of course, the ideal would be to collect material from the nucleus of a comet. It would be fantastic to get a core and bring it back to the Earth, but that's really technologically very difficult. But we can do the second best thing. Rather than trying to bring back those ices and vaporizing them or damaging them, is to go to the comet, land on it and study them in situ.
Well, we haven't actually done that yet, but we have at least blasted a crater in the comet, the Deep Impact mission, Comet Tempel 1. Now, that did make a major crater.
It did, and it made a very big plume of material came out, and the spacecraft that was in close proximity was able to study that plume of material. Unfortunately, it couldn't actually see the crater that was formed, but I think we're going to get an opportunity to have a look at that.
Yes, the hope is that the Stardust spacecraft, which has now safely delivered its primary objective, which is the samples to the Earth, it carried on flying around the solar system, and it can be redirected to have a close encounter with Tempel 1 and be able to, if you time it just right, sample the location of the crater, which gives you an opportunity of studying the interior structure of a comet.
Comets may be spectacular, and of course they bring with them dusty particles which may dash into the upper air and burn away, causing what we call meteors or shooting stars. And meteors are cometary debris. But we also have much larger bodies which come through the atmosphere and land intact and may make craters. And these are meteorites, and they have nothing whatever to do with comets.
No, they don't. We believe that they are fragments from the asteroid belt, so they're much rockier and much more solid. And that in itself is one of the characteristics, is that the atmosphere sorts the meteorites, so the really tough, strong ones come through and land. And perhaps some of the more friable material, which is similar to cometary material, is actually burns up in the atmosphere and just produces dust.
You have a nice collection here.
Perhaps we can start with this one, which is Gibeon. It's an iron. It was found in Namibia, and it's a beautiful stone.
It is.
It's incredibly dense, and one corner here has been cut off, and just to reveal the structure. And when you cut the surface, you can see a very unusual pattern called the Widmanstätten pattern, and we can see that better on this sample here, which is a palisite. This is the stony iron meteorite, and you have crystal grains here, but most of it is metal. And then you have the beautiful Widmanstätten pattern on the outside, which forms as the iron cools very slowly in the core of an asteroid.
And these patterns are found only in meteorites.
They're found only in meteorites, and in fact they're only found in meteorites rich in iron, so stony irons and irons like this.
How old are these things?
Well, they're basically, the iron meteorites most recently have been dated, and they're some of the oldest objects in the solar system, 4.5 billion years old.
And you've got some more here.
We've got some other ones here. If we go to the opposite extreme, we've got here a meteorite called Cameldonga, which was found in Australia. And this is a eucrite, and we believe that this is a sample from the asteroid Vesta. Vesta has a very unusual reflectance spectrum, and it matches the composition of these particular meteorites. So there's very strong evidence that this is actually a sample from the asteroid Vesta. This particular example is quite nice. You can see the central part is actually quite light. When on the outside you can see what is the very glassy, dark fusion crust. And that's formed as the meteorite enters the atmosphere. It starts to melt, and as it melts, the liquid material is sent away from it, and the heat goes out with the liquid material. So the actual meteorite itself stays very cool. And that's important because it means that the meteorite itself is preserved in a very pristine state for study.
And there are some here that you believe came from Mars.
We have, in fact, a sample here of the meteorite Nakhla, which fell in 1911 in Egypt. And it's reputed, although it's disputed, that it killed a dog.
Yes, I think that's really been discounted.
I think it has, yeah, but it's a nice story all the same.
That might be a bit of Mars.
That's what's believed. There's lots of reasons for believing that, and in particular because the composition of some of the material in there matches the observations of the Viking landers in the 1970s.
I once found a meteorite myself. On Christmas Eve 1965, a meteorite shot over England, exploded, and showered bits near Barwell in Leicestershire. I went a couple of days later, with a large clamp and I found this piece, which I handed straight over to the museum, I must say. And there you are. There it is, a bit of Barwell.
Well, it's an ordinary chondrite, It's one of the most common types, but it's a beautiful specimen. And again, you can see the contact. Here's the fusion crust, the outer rind, and you can see it's very different from the interior, which is actually quite light-coloured. And actually, the other thing that you can see on this specimen, are these rounded areas, which are called chondrules. And that's what gives it the name chondrite. And those were believed to be free-floating in space prior to the formation of the meteorite. And they were believed to have formed very shortly after the start of the solar system, about 2 million years after the start of the solar system, so very ancient objects.
Well, look, you're a comet man, you're a meteorite man. Something hit Siberia in 1908 and blew pine trees flat over a large area, and no crater was found. And some people say it was a meteorite, and some say it was an asteroid, some say it was a comet. Well, what do you think, Simon?
I wouldn't like to say which it is, but what's obviously clear is that it was a very fragile object because it didn't survive to reach the ground, even though it was probably at least 50 metres in diameter. And this, I think, illustrates the difficulty we have. Although we can do fantastic things in laboratory with meteorites, there is a large collection of extraterrestrial material which is hitting the Earth but never survives to the ground for us to study in the laboratory. And so if we want to study that kind of material, that fragile material, which incidentally we believe is the most primitive material, we need to be able to go out and get it.
Like it didn't hit a city, isn't it?
It is. We're being hit all the time by material from space, and it's an event which we shouldn't be surprised about, that new things happen. I mean, the material from Tunguska was obviously a very unusual meteorite. This is the meteorite in Siberia. And we should never be surprised by the fact that the material that's arriving from space is strange and unusual.
What about this latest report from a meteorite landing in Peru?
Well, this was a report a few months ago of a meteorite near the Peru-Bolivia border, and it produced a small crater, and the local people suggested that they had been made ill by something coming from the meteorite. This has been largely disproved, but the meteorite itself has now been collected and analysed, and again it's an ordinary chondrite, but a very large ordinary chondrite, which is why you had the pit. And the suggestions that it was an unusual type or that it caused some problems for the people's health is untrue, but the size of the meteorite is very unusual. It's a very large body.
The term meteorites is reserved for particles which actually reach the Earth. They're known as meteoroids. And there's no difference really between a large meteoroid and a small asteroid. And the asteroids themselves go around the Sun, mainly between the paths of Mars and Jupiter, but some may swing closer in.
That's right, and we believe that the fragments which fall to Earth as meteorites are actually fragments of these near-Earth crossing asteroids. And our understanding of what's in the asteroid belt essentially comes from our meteorite collection.
And we have now one spacecraft on its way to two asteroids, the brightest one, Vesta, and the largest one, Ceres.
That's right, and as we said, we think we have samples from Vesta. These are the so-called HED meteorites. And of course, the great thing now is that we've got a spacecraft that's going to go and map it in detail, and we can have a look at the structure of Vesta, and hopefully we can tie in these meteorites with Vesta itself. But we're going to learn an awful lot more about Vesta.
The large ones keep out of harm's way, but some swing inwards. We're going to hear a great deal, I think, in 20 years' time of Apophis.
Yes, that's right. This is one of the many objects that attract because of the certain knowledge that at some point in the past and certainly in the future, objects large enough to have a really catastrophic effect on civilization are going to hit the Earth.
This one's half a mile across, and we'll come close.
Yes, in fact, it's since we've been looking seriously, this has been the highest risk object, and at one point there was a probability of about 1 in 40 that it would hit the Earth. Now we know that's not going to be the case. That was going to be in 2029, but it will pass extremely close, just a little more than an Earth radius away from the Earth, but we're certain now it will miss. However...
Yes, quite. There's a but, isn't there?
There is a but, because when the asteroid flies past the Earth, it's so close that the Earth's gravity will deflect it, and so it changes its future orbit. And that deflection, of course, magnifies any small uncertainty in our knowledge of its current position. And there are certain places which you can fly past the Earth in 2029, which will result in hitting the Earth in the future.
And of course there are other asteroids of the same kind, but they haven't found yet.
There are several thousand objects bigger than a kilometre in size but there are many tens or hundreds of thousands of sizes of 100 meters or more, which can still do catastrophic damage. We only know of the orbits of a tiny fraction of those bodies. And so continually the skies are being searched to identify them and work out the orbits to see which one of those might be the one that hits us next.
What about the origin of these things? How do they get there? Is it cosmic debris, influence of Jupiter? How?
The belief is that the asteroid belt was basically a place where a planet should have formed, but it didn't as a result of Jupiter. And in fact, when you measure the mass of the asteroid belt now, it's very, very a small fraction even of the Moon's mass, whereas originally it was believed to have had almost an Earth's mass. So what we've got in the asteroid belt now is just a tiny remnant of what would have been there originally. And there is also the suggestion, in fact, that some of the material in the asteroid belt didn't originate there at all. In particular, the iron meteorites may well have migrated from the Earth-forming area, from the terrestrial planet area, into the asteroid belt. So when we look at the asteroid belt, it's very depleted, and also some of the material didn't actually originate there at all.
And looking much further out, we've talked about the asteroid belt, but you know now there's another whole swarm of small bodies out beyond Neptune, of which the largest is Pluto, and Pluto is not really a planet.
No, and there are very likely a number of Pluto-sized bodies further out.
Well, one, Eris is larger, isn't it?
Exactly, we've already discovered one at a greater distance. These bodies are almost certainly the source of most of the short-period comets that we see. So things like Comet Holmes. And they are the remnants of this planet-building process in the outer solar system where the density of material was too low for a planet to form.
What's Pluto like, do you reckon? Smaller than our moon, but icy?
I think it's correct, although there's a lot of debate and discussion about demoting it from planetary status.
You've got to.
I think you have to. Not so much because it's different from the other planets, because it's predominantly icy, although there will be a rocky core, but because it's not unique in its region. It's one of many, yeah.
Discovered way back in 1930 by my old friend Clyde Tombaugh. We did a programme about it much later. And we thought then it was the only one, but of course it's not. I'm afraid you've got to demote Pluto.
I think so, yes. Which doesn't make it any the less interesting.
Oh, no. And of course, the one probe on its way there now. New Horizons will pass by Pluto in 2015.
That's right, and it's unfortunately only a flyby mission, so we will get a very quick snapshot of the Pluto and its satellite as we fly past. But of course the mission will carry on into the Kuiper Belt and hopefully fly past other objects too, which will be just as interesting.
But we have had one landing on an asteroid. We had an asteroid on Eros.
Yes, this was not a planned landing.
No.
The probe was designed to orbit the asteroid, study it in detail.
Eros can come within 15 million miles of us.
It's among the class of Earth-crossing asteroids, but not one which can currently hit the Earth. And it's one of the larger ones, maybe 20 kilometres in size. And after the end of its primary mission, the probe was gently landed on the surface, and so there were measurements taken just coming in to get a very, very close-up view of the surface.
Simon, Richard, thank you very much.
Thank you very much.
Well, asteroids may come close to the Earth and also to other planets. And Mars is well seen now, just past opposition, and still a brilliant object. And two tiny moons, Phobos and Deimos, both less than 20 miles across, almost certainly captured asteroids. Pete Lawrence and Chris Lintott are in my garden, so let's go and see how they're getting on.
Well, Pete, we're here with one of my favourite parts of the sky, the winter sky. We've got Orion there with Betelgeuse. We've got Aldebaran in Taurus, at the horns of the bull, with Aldebaran, the brightest star, and Gemini. And this whole region is dominated at the minute by Mars.
It's almost like an orange triangle up there at the moment.
Well, binoculars don't help very much. To see more on Mars, we need a small telescope.
We've got a fairly small one here, a 4-inch telescope, and this is set up on Mars. So if you want to have a look at the view.
Oh yeah, there you are. The first thing you see is, a red disk. So it's a planet, it's not a star. That's a good start.
Would you say it's red?
Well, it's not as red as I expect. It never is. It's a salmon pink, I suppose.
That's a very good description of the colour.
The next thing you notice is at the bottom of the image, as I look at it, It's definitely brighter down there than the rest of the planet. It looks like it's catching the sun.
Well, you have to bear in mind that you're looking through an astronomical telescope here, so the image is inverted, of course.
So that's the North Pole.
The North Pole you're looking at, and the area you're looking at, which is actually quite large and light, is the North Polar Hood, which is a cloud which covers the North Polar Cap.
And this is, what, springtime in the Northern Hemisphere?
Springtime in the Northern Hemisphere, and what will happen is that cloud, which is covering the North Polar Cap...
Ice cap.
Yeah, ice cap, that's right, will actually dissipate and will reveal the cap underneath.
I can just about see some dark markings through there. It doesn't give up its secrets easily.
It doesn't, but if you spend time looking at the planet, what happens is our atmosphere is very wobbly and very turbulent, and it blurs and distorts the image quite a lot, and it hides these features. But if you do spend time looking at it, you can catch these moments when what we call the seeing goes still, and we can get a lovely crisp view of it, and when that happens all these features will stand out quite clearly.
And you can certainly see a lot of detail with a telescope like this one, but it does help if you have a bigger telescope.
Oh yes, it does.
So shall we cheat and go and use Patrick?
Absolutely. Okay, well here we are with Patrick's famous 15-inch telescope, and what we've done is fitted a black and white camera to it where the eyepiece would normally go. So we're taking the output of that and sticking it on this monitor here.
And there's Mars.
And there's Mars. And that's a pretty good view of Mars, I think you'll agree.
And you see these dark markings. Now they're areas where rock has been exposed by
That's right.
the winds.
As the sand has blown away from these areas, that it reveals the rock underneath, and that's what the dark albedo features are that we can see on Mars. Albedo is a term which is used to describe reflectivity, basically, and the albedo features are thus described because they're dark compared to the other areas which reflect more light back to us.
The first task is to work out where we are, and I brought a map along, so
Right.
that's good. Put north at the bottom, and there's this dark region down here towards the bottom.
Which I think is Mare Echoladium, isn't it?
Yeah, that would make sense, and then that would make this Sabaeus, this feature up to the top left.
The Sinus Meridiani just on the left there as well, which is right on the 0 degree of longitude of Mars, of course.
So those are that's Mars's Greenwich.
Mars' Greenwich Meridian, that's it.
And then, so those are the dark areas. There's also this bright feature towards the right, about on the equator, I guess.
I think we're moving into there.
Yeah, that would make sense. So there you go. So that's the view we've got today. But if we came back tomorrow at the same time, we'd get a slightly different view.
Yeah, that's right. I mean, if Mars rotated once in 24 hours, if we observed the planet again tomorrow night at exactly this time, we'd see exactly the same face.
But it doesn't.
But it doesn't. It rotates in 24 and a half hours, so we see an extra half an hour of rotation in there. And that means that if you view the planet at roughly the same time of night over many consecutive days, you gradually get to see it rotate, so that we get to see all of the features.
And we've just missed the most famous feature of all.
The Syrtis Major, yeah, which is very, very distinctive. Some describe it as looking like a bat clinging to a peach.
And the rest of us describe it as a triangle, but it is obvious through a telescope.
It is indeed, yeah. It's one of the most famous markings on there of all. And
then coming into view, if this map is correct, and I trust Patrick, but if this map is correct, then we have another famous feature coming into view.
We do. It is actually beginning to rotate into view at the moment, and that's the Solus Lacus, or the Eye of Mars, and that's a really fantastic feature because there is a dark spot, if you like, in the middle, and it's surrounded by a dark area. So it does look, if you've got a good imagination, like an eye on Mars looking back at you.
Well, we're already past our closest. Mars is receding.
Oh yes, absolutely. I mean, we had opposition at the back end of December on Christmas Eve, and it won't take long for the distance between Mars and the Earth to start increasing again, which means that the apparent size of Mars in the sky gets smaller and smaller, so these features get harder to see. So if you have clear nights, you've got access to a telescope, now is the time to get out there and have a look at the red planet.
And make the most of Mars.
Absolutely.
Well, Mars is only just past opposition, and there's still a brilliant object in Gemini, so go and look at it with a telescope if you can. And meanwhile, of course, probes are there. Mars Express is going round and round the planet and sending back first-rate pictures. Look at these of Noctis Labyrinthus, once thought to be a lake. See the features there, and by cosmic standards, that surface looks rather young. And, of course, the two rovers, Spirit and Opportunity. Spirit had its problems. It got stuck in a crater, had to gouge its way out, and is now, we hope, on its way to its winter quarters. And on the other side of Mars, Opportunity, now descending into a Victoria crater. And both these probes are sending back amazing pictures, and they've lasted for far longer than anyone dared to expect. So, all hail to Spirit and Opportunity. They're amazing, aren't they, Chris?
They certainly are my favourite probes of the last few years, and the results that we get, particularly from Opportunity over the next few months as it descends into this enormous crater, will be absolutely stunning.
Turn now then to the Sun, and SOHO has now been going around for a complete solar cycle.
That's right. The SOHO's the probe that literally stares at the Sun in a whole host of different wavelengths, and we can now watch the Sun evolve. This is one of its first views from 1996. This is in the ultraviolet, so you're seeing the active regions on the Sun's surface.
Working up to maximum.
That's right. It's not intensely regular. On average, there's an 11-year cycle. So as we go through the years, you'll see that the number of active regions, most of them associated with sunspots, increases, and you get more of these dramatic events, these flares that shoot material away from the surface of the Sun.
Well, the next maximum should be in 2012, but we can't be sure, as you say.
And it's important because it affects our local environment as well. And if you watch these flares, they throw material up into the solar system. And with the help of a spacecraft called Stereo, we can now see these heading towards us. And look at this stunning image from Stereo.
That is amazing, isn't it?
So the Sun is just off to the right of this picture. You can see material that's been thrown off the Sun heading through the solar system towards us.
You've got to remember, too, that the Sun is a star. Therefore, in studying the Sun, we're also getting information about the other stars we couldn't get otherwise.
And equally, we can do the other thing. If we want to know how the Sun formed, we look at other stars in the process of forming. And for years, it's been predicted that just as massive stars begin their life, they should send out jets of material.
Now we've seen one.
Exactly. This is a result from the Spitzer Space Telescope. So the star is right in the centre of the field of view here, and there's a disk about 10 degrees, this dark feature. And then you can actually see this jet shooting away from the centre of the star. I thought we knew this happened, but it's always reassuring to actually see the drama for yourself.
We're learning a lot more about star formation now, and also, of course, about planet formation.
That's right.
After all, our Sun is not the only star to be surrounded by a family of planets. We had 55 Cancri, and now a new one.
That's right, and this is probably the youngest planetary system we know of, because it's not far advanced from this star.
No.
I said this star has this disk. Well, this new system, UX-Tor-A, it needs a new name, but nevertheless, it has a dusty disk, and that disk has a large gap in it. And the gap sits roughly where the planets do in our solar system. And the suggestion is that the dust has coalesced to form planets, which has then swept up the remaining debris. So this is probably the equivalent of our solar system in a very early stage of its evolution. And now we can watch this happen.
Trouble is, we can't see these planets yet. I can be happier when we can, but that lies sometime ahead yet.
Well, hopefully sometime in the next decade we should see. We've already detected the atmospheres of a couple of big ones. That was first done with Hubble. It's been done just this month with the Hubble-Eberly telescope in Texas. So we're getting there. I hope to show you an image of an extrasolar planet in the next few years.
You'll see it. I don't think I will, but you will certainly see it. Chris, thank you very much. Don't forget, it's newsletter time. Therefore, if you want your newsletter, send your stamped addressed envelope to The Sky at Night, Newsletter 108, BBC, Birmingham, B1 1RF. And when I come back next month, we're going to talk about the new results from the innermost planet Mercury, because then the messenger probe ought to have got there. So until next month, good night.